All right, today is our last day of view, and we're going to hit three more function types today. They are exponential, logarithmic, and trigonometric. This trigonometric, that is basically just our sine and cosine functions. So one thing to point out, we won't need it right away, but also just make sure that you have the NC test version of Desmos pulled up, and you're working alongside as needed and using that to support our calculations and some of our graphing problems as well. So the first thing we're going to talk about is exponential functions, and these are really anything that have exponents involved in them. And this is actually the last one we learned about, but the most generic are geometric sequences. All right, they're going to contain some initial value and some common ratio which we multiply by. And if we multiply that that initial value by our ratio over and over and over again, we are going to basically have some formula where we can find any sort of term with raised to some exponent. So if we take our initial value and multiply it by our common ratio and raise it to whatever term we're looking for minus 1, we can calculate any term in our sequence. So for example 1, we want to find the 8th term of the sequence 3, 6, 12. You'll notice that we multiply by 2 every single time. So if I want to kind of start identifying this stuff, my first term, a sub 0, oops, sorry, I just noticed that I had a mistake in that there. It should have been a sub 1. Our first term is equal to 3. Okay, our common ratio, the thing that we're multiplying by every single time, we're multiplying by 2, so that ratio r is equal to 2. And so if we want to calculate any term we want, we would use this generic formula a sub n equals 3 times 2 to the n minus 1 power. Since we're looking for that 8th term, we're going to calculate a sub 8 equals 3 times 2 to the 8 minus 1 power, which is really just 3 times 2 to the 7th power, and that will give us 384 as our answer. Now, we also looked at more specific versions of these exponential functions, specifically with growth and decay functions. They're a specific type that rate a future value that we'll call f of x to some initial value a growth rate r. Remember, we're going to have to convert this r to a decimal. And they track that over time. And the two formulas we had were a growth formula, okay, where we were adding r in our parentheses, and that decay formula subtracting r in that parentheses. But they kind of follow that same format that our geometric sequences do, where we have some initial value a, and we're multiplying it by something over and over and over again, so it's raised to a power. So in this problem, example 2, where we're working with a specific growth formula, a particular bank account provides you with an annual interest rate of 4%. If you invest $1,000 in the account, how much money will you have after 12 years? So right off the bat, I know this interest rate here. This is going to be my rate. Let me just kind of identify that. Since we have 4% as a decimal, that rate is going to be converted, or 4% as a percentage. We need to convert that to a decimal, so we'll divide by 100. The rate will be 0.04. Okay, then we are looking for the initial value as well, right? So if we invest $1,000 into our account, then that initial value there, that A, is going to be 1,000. So with these two things, I can write a generic formula here. My money, my function of x after x years, is going to be equal to A, our 1,000, times 1 plus that rate, 0.04, raised to the x power. And now if we want to calculate it after 12 years specifically, all we got to do is swap out that x with a 12. So 1,000 times, I'm going to simplify this in my formula here, 1.04 to the 12th power. And we can come up with an answer here if we plug that in our calculator, 1,000 times 1.04 to the 12th power. That should get us 1601.03, and that is in dollars because we're dealing with money here. And actually, let's go into Desmos. Let's type that in and just kind of see something cool that we can do. If we type our generic formula in, that f of x equals 1,000 times 1 plus 0.04 to the x, we can actually below that then type in anything we want. If we want to see what it is after 12 years, we can type in our f of 12. You'll notice that gives us 1601. If we want to see what it's like after 50 years, we can type that in as well, f of 50. If you had kind of skipped that portion and just gone with wanted to plug in 12, all we got to do is replace that x with 12 in our formula, and you'll see that it calculates out to that 1601 as well. After we talked about our different types of exponential functions, we talked about how we could undo them with logarithms. Logarithms are basically kind of the inverse operation of exponentials. So if we're given something in exponential form, we have a base raised to some power. That's going to give us an answer. We can rewrite that as a logarithm, listing it as log base of b. Our answer then goes inside of our logarithm, and the answer to the logarithm is actually our exponent. Notice how b, x, and n just flipped around. These are used so that we can undo exponents and answer the question, what power? So when we evaluate logarithms, oftentimes we are just evaluating or answering that question, what power? So if I'm trying to evaluate log base 2 of 8, I'm trying to think about, all right, base 2 to what power equals 8? And in this case, I would be 2 to the third power equals 8. So our answer here is going to be 3, right? We would need to go 2 times 2 times 2 to get 8. Similarly, we could try this with another problem where it's pretty easy to do mental math with. We have base 5, raise it to what power to equal 625. If we work through that, I think we would need 5 times 5 times 5, get us 125 times another 5 would get us to 625. So in this case, we used 4 of them. So our answer here, log base 5 of 625, would be 4. Now, it's pretty easy to do that when we have clean numbers like that, where the bases and the exponents and the answers all line up. But for more complicated logarithms, we can use our changing the base formula. For this, we have some logarithm here, log base a of x. We can rewrite this as a fraction or a division problem with a brand new base b. All right, and notice when we do this, the x slides up top, and that base a slides on bottom. When we do this, we want to use the base 10 logarithm or common logarithm because it's programmed into our calculator. So in order to do this in a problem in example 5, sorry, I got distracted there. In order to do this with example 5, where we don't have a clean number, right? If I go 6 to the first power, it equals 6. 6 to the second power equals 36. 6 to the third power equals 216. I overshot that 40 that I was looking for. So instead, I can use this change the base formula, rewrite my problem as a division problem. So equals a new one with log base 10. I'm not even going to write the base in, over log base 10. And I don't need to because it's that common logarithm. And that 40 slides up top. that 6 slides on the bottom. And if I actually do that problem and use division there, or we can go into our Desmos, and we can write in log of 40 divided by log of 6. Okay, we'll get an answer 2.06 if I'm rounding to 2 decimal places there. So 2.06. Now, same thing with log base 4 of 3.5. We can change the base here, rewrite this as log of 3.5 up top, divided by log of 4. And if I go into Desmos and work through that, just change these numbers in my past equation, log point 3.5 up top and log base 4 on bottom, I get 0.90 as my answer. So I will write that there, 0.90. Now, logarithms can be used to help us solve exponential equations. It may not be easy to see what our answer is for this exponential equation here. One thing you can do, though, if you run into this, feel free to throw it in our graphing software, right? We can go 5 to the x minus 2. Oh, again, my exponent didn't stay up there. X 5 to the x minus 2 up top, and 32. And we'll need to set that as f of x equals 32. I could throw that as two different graphs, scroll up, look for my intersection there, and know that my answer is going to be 4.153. But I can also solve this more manually. So if I rewrite this as a logarithm, okay, take my log of base 5 of 32, and then set that equal to my exponent, x minus 2, then I can evaluate this problem out. So if I use my change of base here, this would be log of 32 divided by log of 5 equals x minus 2. And I can either evaluate that number and add 2 to it, or I can leave it like this for now, which I will, just so you can kind of see how this works. I'll add 2 to both sides, add 2 to that side there, so then we get log of 32 divided by log of 5 plus 2 equals x. Ooh, yikes, that's a bad 5 there. Then we can actually go through and evaluate that. I'm going to plug that in Desmos. So we get log 32 divided by log 5. And we are adding 2 to that. It looks like we get 4.15, which is exactly what we got in our graph as well. So that is what x is equal to, 4.15. Another way you can do that if you want is you can take this log 32 over log 35. You can calculate that right away if you wanted to and just round it as you finish the problem. That would be 2.15. If you add 2 to it, you'd get the same answer. All right, we are going to move away from exponents, move away from logarithms to talk about kind of the final big unit we covered, dealing with sine and cosine. So let's ground ourselves back into where these came from. Sine and cosine functions describe the height, sine of our triangle, and coheight, cosine of our triangle as it rotates around the unit circle. So if you look at this image here, sine is our height, cosine is our coheight or our width, and the radius on our unit circle is always 1. So these values are programmed in our calculator, but we need to make sure we are using the right units. If you're using Desmos, which I recommend, go to the settings bar, and you'll notice that we can toggle between radians and degrees over on the right side here. We want to make sure we're in the right thing. If you're in your calculator, you're going to use the button called DRG to toggle between those two things. If we're evaluating these functions, it's as simple as plugging them into our calculator as long as we have the units set right. If in problem A here I have cosine of pi over 6, That's a radian measure. Radians are going to have pi in our measurements. So I check my calculator, make sure I'm in radians, and then it's as simple as typing in cosine of pi. We can type in pi divided by 6. And it gives us an answer there. We're going to round to 2 decimal places. We're going to have 0.87 as our answer. Now, there's another radian measure in these problems. B looks like it's using degrees. C looks like it's using degrees. D is using radians. So I'm going to keep my Desmos in radians right now. And I'm going to type in the answer for D, sine of 11 pi over 6. And that comes out to negative 0.5. Nothing around there. Just got to go and write that answer in. And make sure to pay attention to precision here. We have our negatives. Now for problem B and C, notice that we have this little degree symbol. We're calculating it in degrees. So I want to change my problem over to degrees. And watch as I do this. As I change it to degrees, those values in my previous calculations just changed, right? So it's important to make sure that we are using the correct units of measure when we do that. So I'm going to leave this. I'm going to cancel my old calculations, throw it back into degrees, and the sine of 314, simple as sine 314. Boom, I get an answer. The cosine of negative 130, cosine, negative 130, boom, I get an answer. So it looks like I have negative 0.72 for my sine, negative 0.72. And for my cosine, it looks like I have negative 0.64. And again, I just want to point out, if I go back to Desmos and I change these units again to radians, notice how the values in my equations change. So we want to make sure we're using the right units for our angles. So radians and degrees, they're both ways to measure angles. We can jump back and forth between them. The things to remember if you forget these formulas is that 2 pi radians equals 360 degrees, right? That's one full rotation of a circle. The more simplified version in how we use this is that pi radians equals 180 degrees, and that's what drives these two formulas over on our left here, where degrees equals radians times 180 over pi, and radians equals degrees times pi over 180. So if we're converting radians to degrees here, all we do is say that, hey, 2 pi over 3 times 180 over pi, that's going to be what my degrees equals. Notice how we have a pi on top and bottom, so we can cancel it out. Then we just go into our calculator, 2 times 180 divided by 3. That will give us 360 divided by 3, which is just 120. That is our answer in degrees. If we're going the other direction, converting degrees to radians, we're going to use this other formula. So we use our 150 times pi over 180. And we want to leave pi as part of our answer. So we just want to simplify this down into simplest form. I'm going to start by dividing out 10 from top and bottom, so I get 15 pi over 18. Then I notice I can divide out a 3 from top and bottom, so I get 5 pi over 6. And that is as simple as I can take it, so I'm going to stop it right there. All right, last thing to deal with our sine and cosine is the graphs that they have. So as we rotate around that circle, as we trace around that circle over time, we create this waveform from our sine and cosine value, where we basically repeat over and over and over again with a steady height. They have 3 main features. We have the midline, which is our kind of line of symmetry on our waveform. We have the amplitude, which is the height. Notice how it's the height from the midline to the peak, or the midline to one of those valleys. It's not the full height of the wave. And then our period, where we are tracing from one point, going one full rotation, and repeating it is going to be our period. So we can find that a few different ways. Maybe we trace from the midline down and up back to midline. We'll go over that in our example problems. So with our formulas, A is tied to our amplitude, and that is just a direct connection there. B is going to change our period. Remember how it doesn't actually line up with our period? We have to calculate it. Period equals 2 pi divided by B. And finally, that D is going to be our vertical shift of the midline. So when we write our equation of the midline, it'll be y equals D. So let's use our equation in example 11 to identify these features first. So we get a function, it's 5 cosine, that should say 6x minus 4. And we could graph this if we wanted to. We could say, hey, our f of x equals 5 cosine 6x minus 4. And we'd want to make sure that we are in radians. That is the default setting for our sine and cosine graphs, is to be in radians unless otherwise noted. We could go ahead and find all this stuff from the graph if we wanted to. However, we can find it from the equation really quick as well. Our amplitude is just that a value out in front, so it's 5. The equation of the midline is tied to this shift here, so y equals -4. And if I throw that on our graph, check this out. If I throw in a separate line, y equals -4, notice how it creates a nice line of symmetry there on our graph. And finally, the period, we're going to need to calculate that. So if I have b is equal to 6, right, this is my b value. My period is going to be 2 pi over b, so 2 pi over 6. You're not wrong if you leave your answer like that, but we should try to simplify it down to the lowest fraction. So 2 pi over 6 is the same as pi over 3. And probably more importantly than reading these from the equation is the ability to read these from our graphs. It looks like I'm going to have to zoom out just a little bit on this so you guys can see everything that I'm working with. Maybe a little more. And let's go one more time. Okay, so let me clear the selection out. In this first graph below, we are going to identify the midline, the amplitude, and the period. So that midline, we want to try to find the line of symmetry that our wave is kind of passing through. Sometimes the midline is noted as the y-intercept. Other times it's not. It looks like it is here, where if I trace this line from 2, I'm creating a nice line of symmetry on my graph. So I'm going to say that y equals 2 for our midline. Our amplitude, we measure up from our midline to our peak, or we can measure down. Either way, we're going to get the same thing where we travel 1 unit, 2 units, so our amplitude is 2. And that period, some of you really liked finding a peak-to-peak distance, where we took the 5 pi over 2, subtracted pi over 2 to get our period, but other people really liked starting from the start, tracing one full rotation. Notice I'm back to center, but I haven't traced one full rotation. We go up, then down, then back up to center. And noting that, hey, I land at this 2 pi here, so that is my period. Let's do that real quick with example 13 before we find the other things, all right? If I start at the start of my graph here in example 13, trace one full rotation, so I'm up, I'm down, I'm back to where I started. That happens at pi, so our period is pi. The rest of the stuff, we can find just the same as before. So our equation of the midline, look for that line of symmetry. It looks like it also happens at 2 here, where we have that line of symmetry. So y equals 2 for the equation of the midline. And if we measure our amplitude from the midline to a peak or a midline to a valley, it looks like it only goes 1 tick. So our amplitude is just going to be 1.